at any 2 points, the potential difference at any 2 points VAB is minus integral A to B E bar dot dl. And for absolute potential, it is minus integral infinity to your observation point, to your final point P, E bar dot dl. And the relationship between them was VAB is VB minus VA. Then we took an expression, we took an example, find the potential which can be created by a point source which is placed at origin. And then we saw that it is Q over 4 pi epsilon R. And if it is not an origin, this is the expression. So remember, compare the electric field. If we compare the electric field of if we compare the electric field of a point charge placed at origin and the potential due to that point charge placed at origin, you know what you can see? We can see that the electric field, its magnitude goes down as a function of 1 over r square, where r is the distance between your observation point and your charge, which is at origin. But the potential, if you see, it is over r. So electric field falls quickly compared to the potential. So potential falls as a function of 1 over r as you move away from the charge, whereas the electric field falls as a function of 1 over r square. Then we took an example. We took the potential due to several charges and charge distributions. We took a good example on this one. And lastly, we stopped here saying that the circulation of our electric field along any closed path is equal to 0. And as I told you, any vector field which satisfies this, that vector field is called as conservative. So that's why our electrostatic field is conservative. So whichever path you take, whether you take path 1 or whether you take path 2 here, whether path 1 or path 2, whether you take, it is independent of the path. And because of this, you will see that if you find the electric field along any closed path, then we see that it is equal to 0. So we are using closed path. That's why I'm putting this a circle here. That is, this automatically says that it's a closed path. That is, the circulation of electric field along a closed path is 0. So this is where we stopped. Now what we are doing is we are now just trying to get the same expression that we got here. We got it in terms of the line integration. Can we just try to get it in terms of surface integration? And this is possible. Which theorem we can use? Which theorem will relate the line integration to the surface integration? Stokes theorem. So divergence theorem relates the surface integral to the volume integral, whereas Stokes theorem relates the line integral to the surface integral. So we are applying for our electrostatic field, and we are saying that if the closed line integral of my electrostatic field dot dl along a closed path is equal to, is nothing but it is the curl of that electrostatic field over the surface ds, and this surface is enclosed by that closed path, is nothing but the the curl of that electrostatic field over is the surface integral of the curl of the electrostatic field over the surface which is enclosed by the closed path. That means if this is my, sorry, so if this is my closed path that I have used, okay, So this is my closed path. So I did a line integration along this closed path. And let us suppose that this is my electric field moving in this manner. Like this. This is my electrostatic field E bar. So if you integrate this electrostatic field along this closed path, it will be 0. And if you apply the Stokes theorem, what it is saying that this will be same as you take the divergence of this electric field and integrate it over the surface. See, this is the surface and this is the surface area which is enclosed by our closed path, right? So because this was my closed path, so the area which is enclosed by my closed path is this area. So if you do the curl of the electric field and if you integrate over the surface, it will be the same. This is your Stokes theorem. And if you apply that Stokes theorem here, then this del cross E bar dot ds over the surface is equal to 0. And then if we, since the left hand side and the right hand side must be equal to 0, that means the one which is inside the bracket, which is the curl of the electric field, becomes 0. Very important relationship. Curl of electric field is equal to 0. That means an electrostatic field is curl free. That is, the electrostatic field doesn't have a tendency to rotate. It doesn't have a tendency to rotate. So this is a very important property of electrostatic field. Okay, this is the important property of electrostatic field. So now I'm summarizing whatever we have studied so far. We have studied two very important fundamental laws. The first one was the Gauss's law. See, Gauss's law. So closed surface integral d bar dot ds bar is equal to the charge enclosed q. This is in integral form. This is in differential form. Del dot d bar is equal to rho b. Now the second important law that we have found is the circulation of the electrostatic field along a closed path is 0. This is the integral form. And in differential form, it is del cross E bar is equal to 0. So any vector field, if they satisfy these two laws, that vector field is nothing but an electrostatic vector field. Okay, so this is our two laws. Now let's continue. Let's go to our next lecture. So lecture 6. So here what we are doing is, yes, we got an expression of the circulation of electric field. Now what we are doing is we got this expression, right? That is the potential, the relationship between the potential and the electric field. That is, the potential is nothing but minus integral infinity to my final point A E bar dot dl. So this is one expression where the electric field is given to us, then I can find the potential. Now, what we are doing is, now we are interested in finding an expression where if a potential is known to us, can we find the electric field which has resulted, the electric field which is responsible for that potential? This is what we are trying to do. And, it's very simple, very straightforward. So what we are doing is, we are again considering, say, 2 points, VA and VB. So VAB is VB minus VA. It is minus integral A to B E bar dot DL bar, which is our potential difference. And now what I'm seeing, taking is, I'm taking this 2 points A and 2 points B. And I'm assuming that this point A is X, Y, Z. And point B is a little bit away from point A. And this is your delta X. Okay, then so VB minus VA. So VB minus VA, the potential of VB. So what I'm doing is I'm now finding VB minus VA. So what will be VB minus VA is nothing but the potential at this point. So which is X plus delta X comma Y comma Z minus potential at this point, V of X comma Y comma Z, right? Now, what we are doing, we are also trying to find this VB minus VA using, so first we used this expression. Now we are using this expression. So VB minus VA is nothing but the potential at this point minus potential at this point. So if I apply the right hand side, so the right hand side will be minus integral a to b e bar dot dl. Now what is the integral? What is the a and b point? So the a and b point is only the variation is with respect to x, because they are only, you know, elemental distance away from each other in the x direction. We have assumed it for simplification in x direction. So therefore I can say that this integration will have the limits from x to x plus delta x. Okay, x plus delta x. And therefore, if I do this e bar dot dl bar, only the x component will be left, because the integration is only for the x component, because this is my own x direction. And therefore, I will get just this. In this one, I will get only ex left. In this one, I will only have dx left. And the dot product of them will be ex multiplied by dx, which is nothing but this integration of x plus delta x times ex dx will be what? Is nothing but minus ex times delta x. This is almost, see, this is approximation sign. It's minus ex times delta x. So this is the answer that we got with this integration. And this is what we have from this equation, and both are same. So if I equate this, and if I move this minus on this side and delta x on this side, I will get ex is approximately equal to minus of the potential at this point minus the potential at this point over delta x. And if I want to remove the approximate sign, then this delta x, the elemental distance between these two, I have to bring it close to 0. That is, limit when this delta x tends to 0, then this is your expression. So the approximate sign is changed to equal sign. And what is this? Limit delta x tends to 0, v of potential at this point minus potential at this point over delta x. This is nothing but, this is the definition of the differential. This is the definition of the partial differentiation with respect to x. And therefore, your ex component is nothing but minus dou v over dou x. And similarly, we can also go and do it for y and for z. So therefore, we will get dou ey as minus dou v over dou y and ez as minus dou v over dou z. So that means my e bar is nothing but is if I put all these ex, ey, ez together as a vector, because an electric vector, I am considering it as ex ax plus ey ay plus ez az. So my e bar is equal to minus dou v over dou x ax minus dou v over dou y ay minus dou v over dou z az. And therefore, your e bar is equal to minus, and what is this one? This minus del operator. So it is minus del v. This is the expression. So this is the relation, again, another relationship between the electric field and the potential, which is E is equal to minus del V. So I explained it from this point of view, and in your book, it is also explained in a very similar manner, but there they have used the calculus of multivariables, and then they did it in a very similar manner. So it's both are, equally correct approaches. But in the end, you are getting E is equal to minus del V. So till now, we have two expressions. So first expression for the potential is in the integral form, which is VA is minus integral A infinity to your final point A, E bar dot dl, or another one, which is E is equal to minus del V. So though both these expressions are very handy. So this expression can be used when electric field is known to you, and then you need to find a potential at a particular point. Then you can use this expression. This expression becomes very handy when you know the potential, how the potential is varying in an open free space, maybe free space or in any material, anything. So if you know the potential, how the potential is varying, because potential is a scalar, so you know how the potential is varying in any coordinate system or in any space, then can you find what is the electric field which is responsible for that potential? That you can use this expression. E bar is minus del V. So there is an example here. So this example is allowing you to find the electric field when a potential is given to you. So see here. So the example is saying that consider the following electrostatic potential that is existing in free space. So in the free space, a potential is existing, which is a scalar. And as you can see, it's a function of R. So it's a function of R. So you can now think it in spherical coordinates, that this is the potential, and this potential is now in that spherical coordinate system. Now what we need to do? We need to find the expression for electric field intensity. By the way, see this potential expression is given to us. Now you can go and you can find the potential anywhere in free space because this expression is known to us. So for example, what will be the potential at the point? What will be the potential at the point, say 2, 30 degrees, 50 degrees? What will be the potential? Just
e to the power minus 4.
Yes, so it is e to the power of minus 4. Or 2, 10, 80 degrees. Again, it will be the same thing because your potential is not a function of theta and phi and theta. It's not a function of all these things. So you can find the potential anywhere in your free space. So here our objective is that you need to find the electric field intensity. That is, you need to find the electric field who is responsible for this potential. And then you also need to find the electric flux density also, who is responsible for this potential. Then we also need to find the charge, find the expression of the charge distribution responsible for this potential. So who is the source, who is the charge, who is responsible for this electric field and electric flux density and also this potential. So now we are going backwards. If you see in Coulomb's law, in Gauss's law, the charge, the source was known to us. And from the source, we were finding the electric field and then we found the potential. Now we are going backwards. A potential is given to you. Can we find which electric field is responsible for this potential? And then can we find what is the source, what is the charge distribution that is responsible for this potential and which is responsible for this electric field? This is what we are trying to, find here. So, and then you have D and E. So D and E, when it comes, we will talk about it. So that's fine. First, find the expression for electric field intensity. So now think about it. You have the potential and you need to find the electric field intensity. So what expression should I use? So V is known and E we need to find. So which expression should I use? So I know two relationships between them, right? So first, VA is minus integral infinity to A E bar dot DL bar, and another one is E bar is equal to minus del V. So which one should I use? So see, this is how you have to, think. Now V is known to us, I need to find E. So this will be difficult because this you don't know. But here, this you know, and you can find E bar. So therefore, you can use this expression to find the electric field. This is what we are doing here. So therefore, because now we are in spherical coordinates, right? Because when I look at the potential, I can easily figure it out that the potential is given in spherical coordinates. It's a function of R. So therefore, my del operator that I should use to find the electric field will be in spherical coordinates. So it should be minus dou V over dou R AR plus 1 over R dou V over dou theta A theta plus this one. So if you substitute V in this one, you will see that your electric field is 2R e to the power of minus R AR. So your electric field is equal to 2R e to the power of minus R square AR. That is, your electric field is a function of only R, and it has only one component in the R direction. Now, can you find the electric flux density? Because this is part A. Part B, electric flux density, yes, is epsilon E bar. And since it is already given to us that it is in free space, so it will be epsilon naught. So therefore, only adding epsilon naught. So 2 epsilon 0 R e power minus R AR. This is the electric flux density. So this is the electric field, electric flux density, which is responsible for that potential. Now, next, see, now we need to find the charge distribution. So how can you find the charge distribution when potential and electric field is known to us? Now let's go back and look at what we have. So we know E bar is known to us, V is known to us. Now we need to find charge distribution. Charge distribution, I mean we need to find rho V. Again, remember guys, I have already told you that sheet and line, these are the special cases, but the more general distribution will be rho V. So now here, because we don't know how the distribution will be, so we will go and always take the more general case, which is the volume distribution, rho V. This we need to find. Now, how can I do this? So try to see if there is a relationship between these two, or if the relationship between these two. Now, relationship between potential and rho V, no. Because till now we have seen that from the charge distribution, we always try to get electric field. And then from the electric field, we can get the potential. So this relationship we don't have, but this relationship we have. And what is that relationship? Yes?
Gauss's law?
Gauss's law. Yes, the relationship is Gauss's law. Gauss's law. Now we have again, so we have identified this. Now we have two ways. So use Gauss's law in differential form, in integral form, or use Gauss's law in differential form. So which one will you use? Which one is more easier? Which one is more handy for you?
Differential.
Yeah, so we know it very well. Usually the differentials, are much easier than integrals. So therefore, it's better to use the Gauss's law in differential form. So that's why it is del dot d bar is rho v, and just find the del dot d bar, that is the divergence of d bar. So if you find the divergence of d bar again in spherical coordinates, you will see that the distribution, the charge distribution rho v is again a function of r, and it is equal to 2 epsilon 0 3 minus 2 r square e to the power of minus r square. This is the expression. And by the way, if you use the integral form also, you will get the same answer. But now the only thing is you need to identify the easiest approach. So the easiest approach is this one. This approach is difficult. This approach is difficult. So you got the charge distribution which is responsible for that potential and electric field. Now, next, what is the total charge enclosed in it's A? So what is the total charge enclosed in a spherical volume of radius A centered at origin? So now this is our charge distribution, right? So our charge distribution is a function of R. So our rho v is a function of R. So it's a non-uniform charge distribution. See, this is an example of a non-uniform charge distribution because it's a function of R. Now, what it is saying that I have a small spherical volume. So if I consider the small spherical volume, what will be the charge enclosed in that spherical volume? Because this charge distribution is now again everywhere. You can think that it is everywhere because it's a function of R. Now, if I have a small spherical volume of radius A centered at origin, how much will be the charge enclosed in that spherical volume? This is what we are trying to find. So how you can do it? You know the expression very well, very easy. So the charge is nothing but integral over the volume rho v dv. So rho v, the volume, volume charge density. The volume charge density is known to you. This is the volume charge density. And you just need to find the integration over V. It's given it as a sphere of radius A centered at origin. So therefore, dV will be r squared sine theta, d theta, d phi, and dr. And what are the limits? The maximum limits. Phi will be 0 to 2 pi, theta will be 0 to pi. And for r, because it's of radius A, so it goes from 0 to A. And if you do this integration, you will get the answer. And that answer you can solve. Now, if you see here, again, you are using this expression. And if you see here, you are ending up with a sort of difficult integration. Can you see this one? Because you have r to the power of 4 multiplied by e to the power of minus r square. So you have to do the integrations by part. So if you use this approach. Now, finding the charge, there is another approach. What is the approach? This was the first approach. Another approach to find the charge is Gauss's law, because we know closed surface integral of d bar dot ds bar is nothing but the charge enclosed. So if I use this and assume that my Gauss's surface, which is the hypothetical surface that I decide, if I make that hypothetical surface as my spherical shell, of radius A centered at origin, if I make it as a spherical shell of radius A centered at origin, then the charge which is enclosed in the spherical shell is nothing but it will be the charge inside the sphere of radius A, inside sphere of radius A centered at origin, right? Inside sphere, the volumetric sphere, I can say it as volumetric sphere centered at origin. Because inside, what volume is enclosed by our spherical shell? It is nothing but the spherical volume of the radius A, and this is what we want. So you have two approaches. When I go to this approach, I got stuck because of complicated integration. This is the second approach. So if we use the second approach, Q is nothing but closed surface integral d bar dot ds bar. And what is my d bar? I know. What is my ds bar? It's a spherical shell. So I will take this, surface. So it is r square sine theta d theta dr. And this is at a fixed r value. R is constant. R is equal to A. And it's because it's a closed surface, the unit normal will be AR for this one. And that's why your D bar, which is your this one. So you have an AR here, and your DS will also have an AR here. So AR dot AR will become 1, and that's why you get simply these two multiplications. And the good thing is you have to evaluate this at a fixed constant R value of A. And therefore, the integration becomes very simple. And therefore, your charge is 8 pi epsilon 0 A cube e power A square. Clear? So, there are several approaches, guys, that you can use to solve a problem. And some approaches becomes very easy to apply and get the answer, whereas some approach becomes extremely difficult. Now, which approach to choose and solve a problem? This comes from experience. This comes from practice. So that's why this is a course where you need to practice. I would suggest you to please go and at least practice, say 3 to 4 problems, in a week at least, review the 3 lectures and go and do 3 to 4 problems from the textbook or from the exercise or from the homework. Try to solve, because the more you solve, the more you will get the ideas. Now the last one is E, and it is saying that calculate the potential difference VAB. So how do you find the potential difference VAB? These are the 2 points. So can I find the potential at this point and then the potential at this point and take the difference? As simple as that. But just one thing, because these are in Cartesian coordinates, as you can see from the points, it is clear that these are Cartesian coordinates, and your V is in spherical coordinates. So you need to do the point transformation. So transform this point and this point to spherical coordinates and then use this expression. So when in the transformation, we only require R. So what will be the R for this point and what will be the R for this point? Yes, if we apply the expressions, the R of this point will be 0 and R for this point will be this one. And if you do VB minus VA, this will be the potential difference. Okay, so this is our example, a very nice example where we have, we came across several ways to approach a problem and identify the easier way to get the answer. So please try to do, more problems. So for example, in your textbook, if you see, there are several examples also which are being done. So we did for the volume. So this is the Gauss's law. So in the Gauss's law for the infinite sheet, for the sphere, we did it in the class. So you see, you have an example here. So try to do this example. So it will be, you will get a good experience. This is an example of a non-uniform charge distribution, because in our notes, in our class, we always dealt with uniform charge distribution. That's why we were able to take rho v always outside the integration. One of the student asked, if it is non-uniform, then you cannot take it. And this is a good example where your volume charge distribution is non-uniform. So you have to keep your rho v inside the integral and do the integration. Good example, so try to, practice, go through this example. For the electric potential, we have some examples for the two charges. We have an example for a point charge and a line charge, similar to what we did it in our class. And then there is one more thing which I wanted to show you, a very good example. I think, yeah, this one. This is before Gauss's law. See, this is a good example. Try to do this example. This example is a ring. See, so you have a ring here. So this is the ring, and this ring has a uniform charge distribution of rho L. So it's not straight. It's in the form of a ring. Then how do you get the electric field? So you are using Coulomb's law here. So, go through this. How would be the electric field looks like? Because we did it for a line charge, we did it for a surface charge, and we did it for a volume charge. This is a different type of charge distribution, ring. And in the practice exercise, you have a disk. Disk is like a plate, circular plate. If your charge is like a circular plate, then how will you get the answer? Good examples, and this will give you a good practice of applying Coulomb's law. Then this is for the finite sheet. And then, you can go through this. This is again a very good example. So see, what is this example is saying? This is an example of two planes and one line charge. So this is a plane x is equal to 2, plane x is equal to -3. They have this uniform charge densities, and you have a line which is placed at here, and it has a line charge density. You need to find the total electric field at this point. So therefore, you need to find the electric field of each of these two planes and these two lines at that particular point. Very good example, and very good application of the formula of the line charge, which is rho L over 2 pi epsilon rho. So how do you find this? How do you find the rho? Because rho is the, we know it. What is, this rho, and, what is this A rho? Or you can go and you can apply the general formula. But here he is applying this formula. This is a very good example, because one of the student asked me that, how you can apply the line, the line electric field expression that we derived for an infinite line, rho L over 2 pi epsilon rho, for an infinite line of a uniform charge density rho L. So this is an example where your line is not placed at a typical location like x-axis or y-axis or z-axis, or just at some height above x-axis, height above y-axis, and height above z-axis. It is now placed in at x is equal to 0 and z is equal to 2. So it is now on the top of this xy plane. So in such case, how can you find rho? So this example is very nicely explaining how do you find rho. So please try to practice these examples from the textbook. The textbook already have several examples, and then you can go to the exercise examples and also our homeworks which we are providing. Okay, so this is again another example of a potential is given to you. you need to find the electric flux density and several other things. And he is showing you two methods, method 1 and method 2. So try to, make use of these examples and then try to solve it. Okay. So now let's go to electric dipole. Now, what is an electric dipole? So this is a special name which is given to this particular configuration where we try to bring or try to place a positive charge and a negative charge, and we try to place both of them at a distance of d. A positive charge and a negative charge separated by a distance d. This is called as a dipole, electric dipole. And this Q and Q, they are of equal magnitude but opposite sign. So this charge, equal magnitude, positive sign, equal magnitude, negative sign. And this electric dipole, they are, they have a parameter that defines the dipole. And that parameter is called as the dipole moment, and which is nothing but it is simply the multiplication of the magnitude of the charge, which is Q, times at what distance you have separated them, D, QD, which is Coulomb meter. So this is called as dipole moment. So this is a parameter that defines a dipole. That is, it gives you the charge and it gives you at what distance it is, the charges are separated. Now, let us try to find what is the electric field which is created by this dipole and what will be the potential which will be created by this dipole. So we are doing both. So this is another example that we have a dipole and the dipole is placed on the z-axis and it is in free space. And we need to find the electric, we need to find the potential at a point P, which is very far from the dipole. And then we also need to find the electric field. So here, this is my dipole. If you see, this is my dipole. So this is my minus Q. This is my plus Q, which is placed here along the Z axis. And the center or the origin is 0, which is here because we are going to use spherical coordinates. So this is my origin. That's why Z is equal to 0. And the distance between these two is D. And my observation point P is here, which is very far. So if you see here, the distance of the dipole, that is from the center to my observation point P, which is your R, is very far, okay, is very far. Now, if it is very far, then this condition is satisfied. That is, my R becomes very much greater than the separation between the two charges. So now, what is our, so this is our problem. So now in order to solve this, what we are going to do, we are going to find the potential, and this is equal to the potential. First, we will find it for the positive charge, then we will find it for the negative charge, and then we will add them. So what I'm going to do for the positive charge, I'm assuming that my distance of this positive charge to the observation point P is R plus, and my distance from the negative charge to the observation point P is R minus. Therefore, if I know R plus and if I know R minus, which is nothing but the distance between the charge and my observation point, which is nothing but your distance vector. You can think it as a distance vector or the magnitude of the distance vector. Sorry, it's the magnitude of the distance vector, R. So, I'm sorry, not magnitude of the distance vector because we are dealing with potential. We are not dealing with electric field. So in the potential, it will be just the distance between the charge and the point P. So for this, it is nothing but Q over 4 pi epsilon naught R plus. So this is for the positive charge. And for the negative charge, it is minus q over 4 pi epsilon naught r minus. That is the distance between my negative charge and my point P. So we only are left with finding r plus and r minus. So r plus and r minus. I think, guys, we have only 3 minutes left, so I don't think we will be able to go through this example. So maybe we will stop here because I have a couple of poll questions. So if we take that poll questions, the time will be sufficient for us. So just let me stop sharing. So yes, so be ready with the poll question. And as I have already mentioned in the Blackboard, guys, you will get you will take 2 to 3 seconds or 4 seconds depending on your internet connection for your answer to capture. So whenever I start the countdown, please don't select just 1 second or 2 seconds before the countdown and then telling me that your answer is not captured. So therefore, please select your answer, at least 4 seconds or 5 seconds before. And when you press submit, your submit button should become deactivated. Okay, so at least, press it 4 to 5 seconds before. So let's start. So this is my first question. And your time is now 40 seconds are there. Very simple. 10 seconds finished. $20 seconds finished. 30 seconds finished. 33, 34, 35, 36, 37, 38, 39, 40. So Gauss's law can be derived from Coulomb's law, and hence it is a fundamental law. It's a true or false? Yes?
False.
It's false.
It's false because we derived Coulomb's law from Gauss's law. So therefore, Gauss's law is a fundamental law, not Coulomb's law.
Doctor,
Yes.
every question 40 seconds, just I want to make sure.
Sorry?
Every question 40 seconds?
No, true or false will be 40 seconds. Multiple choice will be 1 minute. Okay?
Okay.
Okay, this is the last question. So this will be 1 minute, quick. This will be 1 minute. It's a multiple choice. $10 seconds. $20 seconds. $30 seconds. 40 seconds. 50 seconds. 52, 53, 54, 55, 56, 57, 58, 59, 60. So what is the answer?
Outside the sphere.
So it exists, E can exist both inside and outside the sphere because we did this example. Okay, so I think we will stop here and we will meet